We are starting with the next topic of alcohol phenols chapter, acidity of phenols. Before this, we have covered up the primary, secondary, tertiary alcohols and the alcohol and the water behavior in acidic nature. Now we are doing the acidity of phenols. Phenols are acidic in nature. The reason is due to resonance, there are lone pair of electrons on oxygen. So these lone pair of electrons on oxygen are moving towards the benzene ring, and these resonating structures we will get in this lone pair will move towards this side. So now we will have a double bond here, and oxygen has used this lone pair, so it will get positive charge. At the same time, this bond is coming on the carbon, and this carbon gets a negative charge. Now this will move here, this will come here. We know these resonating structures already, we have done this. So here we have a bond, negative charge will come here. Now this will move here, this bond will come out on the carbon. So here we have negative charge now. And the last structure is the lone pair on oxygen atom will come back. So now in these resonating structures, the structures second, third, and this fourth resonating structure. If we'll see these structures carefully, we'll see that there is a positive charge on this electronegative oxygen. This electronegative oxygen has got a positive charge. So due to this, what will happen? This O will become deficient in electrons. So to complete its deficiency, it is pulling the electrons from this OH bond. And as a result of this, what will happen? The release of this H plus will become easy because electrons of this bond, they will be pulled by the oxygen. So if release of H plus is there, that means phenols are acidic in nature. Easy is the release of H plus, more is the acidic strength of a compound. So after doing the acidic nature of phenols, along with this we have a comparison of acidic nature of alcohols with phenols. So out of alcohols and phenols, phenols are more acidic in nature. The reason is, in case of alcohols, if this H plus is removed, we will get this alkoxide ion. This ion formed is called alkoxide ion. And from phenols, if we remove the H plus, as a result of this, we will get phenoxide ion. Now in both the cases, we are getting H plus removal, alkoxide formation and phenoxide formation. Alkoxide ion, and this is phenoxide ion. Now easy is a formation of this ion, that is, this ion is forming by the removal of H plus. So we can say easy is the removal of H plus, more is the acidic strength. Now in which case release of H plus is more easy? That is, in case of phenoxide ion, the release of H plus is more easy. Now how we can say release of H plus is more easy in the case of phenoxide ion? In this case, due to high electronegativity of sp2 hybridized carbon of phenol, to which this OH group is linked. This carbon is sp2 hybridized, while in case of alcohol, carbon is sp3 hybridized. So if this carbon is sp2 hybridized, that means this one is electronegative in nature. Electronegative means this can pull the electrons of OH, of the oxygen, towards its side. Thereby, there will be less electrons now on the oxygen. So oxygen will become electron deficient, but O is electronegative in nature. So to complete its deficiency of electrons, it is pulling the electrons from the H side, from this OH bond side. That means if it is pulling electrons from here, release of H plus will be easy. And release of H plus here is easy. That can be confirmed further, like phenoxide ion further shows resonance, while there is no resonance in case of alkoxide. That means if this is showing further resonance, that means this is stable, and reactions always go towards the stable side. So reaction is easily going towards this side with the release of H plus. That means phenoxide ion is more stable as compared to alkoxide ion. So for this we can draw the resonating structures of phenoxide ion also further. To draw the resonating structures of phenoxide ion, we are taking now O, which has 3 lone pair of electrons with negative charge on this. This is phenoxide ion. In its resonating structures, now negative charge is moving here and this bond comes on this carbon as negative charge. So in this structure, this carbon gets negative charge. Now this negative charge is moving here, so there's a double bond, but oxygen will not get any positive charge here because it's the negative charge which is moving, so O will become neutral. In next structure, this negative charge moves here and this bond comes out on this carbon. So the structure is O, negative charge, and bond. Next structure is like this, just like the previous one only. Second resonating structure, this is the third, this is the fourth resonating structure, and the last one we get this negative charge back on the oxygen. So now these are the 5 resonating structures shown by phenoxide ion. So due to resonance, what happens? There is delocalization of negative charge. This negative charge which is coming on the oxygen, that will get delocalized due to resonance. The delocalization of negative charge takes place, that makes phenoxide ion more stable. That makes phenoxide ion more stable, and thus release of H plus is easy. That is why phenols are stronger acid than alcohols, while there is no resonance shown by alkoxide ion. So after knowing the acidic nature of phenol, the comparison of acidic nature of alcohol and phenols, now next is if we take substituted phenols. Substituted phenols means in phenols we add a substituent. But substituents now are of 2 types. One type of substituent is electron releasing in nature, and another type of substituents are electron withdrawing in nature. Examples of electron withdrawing substituents, mainly in the organic chemistry in 12th class, we come across nitro group. But along with nitro, the withdrawing groups are these also: aldehyde, ketone, even the carboxylic. These are electron withdrawing in nature. An electron releasing example is like the alkyl groups are electron releasing in nature. We can take OH is electron releasing in nature. In case of electron withdrawing character, if electrons are withdrawn by these groups, release of H plus is easy. If release of H plus is easy, that means acidic strength is more. Acidic strength is more. While in case of electron releasing group, they are giving the electrons. So when they give the electron, O will not be so much deficient in electron. So H plus release becomes difficult. And if H plus release is difficult, that means acidic strength in these cases, they will decrease. So if I am taking, for example, this is phenol and electron withdrawing group I am taking. Second example I am taking electron releasing group. So electron withdrawing means this is withdrawing electrons from this oxygen, while releasing means this is giving electrons to this oxygen. So in this case, if this is withdrawing electrons from this, what will happen? O will become deficient in electrons, and if O will become deficient in electrons, it will pull the electrons from this side, and thus H plus release will be easy. While in this case, this R is giving electrons to oxygen. Oxygen is not deficient in electrons here, so why it will pull the electrons from this bond? And if it is not pulling electrons from this bond, that means release of H plus will not be easy in this case. So if electron withdrawing groups are there, they further increase acidic nature of phenols, while if electron releasing groups are there, they are decreasing the acidic strength of the phenols. So this is about the first property of alcohols and phenols that we have done, that is acidic nature. Now moving on to the second chemical property. This is esterification reaction. Esterification means formation of esters. And we know esters are formed by reacting alcohols with the carboxylic acids. So if we react alcohol, we are doing alcohol chapter, so we are first writing alcohol. If we react alcohol with carboxylic acid in presence of an acid, this formation of ester plus water. So if I'm removing H from here, OH from here, this is water, and what is left is RCOOR will be left here. This is ester. But now esters we can also get by reacting alcohols with acid anhydride also. It's not only carboxylic acid, it can be acid anhydride also. In presence of acid, this formation of ester plus this formation of carboxylic acid. So how we get ester here? Let's see, this is RCOOR. This becomes ester. Now what is left after removing RCO? One more RCO is left here because this is whole twice. So RCOO and this H left here, this is forming carboxylic acid. So we are getting ester and we get carboxylic acids here. Now third is if we react alcohols with acid chloride, then also there is ester formation. But the thing is that this reaction takes place in presence of a base, not an acid, and that base is pyridine. So in presence of pyridine, this reaction will take place, and this is RCOOR, ester, and what is left along with this is HCl, H and Cl. Now question here is why we are using pyridine in case of acid chloride. In case of acid chloride, in the reaction only there is acid formation. So if the reactions are in presence of the acid, then what can happen here is that this reaction can go towards the backward side. But this pyridine here, this will neutralize this acid HCl and reaction equilibrium will shift towards the forward side. So the use of this base is to neutralize this acid formed, and then the reaction equilibrium will shift towards the right hand side. So this is the use of the reaction. Now one more question here I am taking up along with this thing is that if we want to introduce acetyl group in alcohols, like this compound is salicylic acid. Salicylic acid. How we can introduce the acetyl group in this alcohols or in the phenols? If we react this with the acid anhydride or the acid chloride in presence of acid here, then this acetyl group is COCH3 group. So it can be by the reaction of acid anhydride or by reacting the acid chloride, because both these contain this RCO, that is the acetyl group in them. This compound is called acetic anhydride. And remember, this reacts with the OH group, with alcohol. This H comes out. In place of this H, this COCH3 will be here. So COOH. O, in place of H, which group will come here? Acetyl group, COCH3. And after removing this CH3CO, one more CH3CO is left. So CH3COO and this H, they combine to form this acetic acid here. So this introduction of acetyl group in the OH, that is in the alcohol or phenol, this reaction is known as acetylation reaction. Name of this reaction is acetylation reaction, and this compound is called acetyl salicylic acid, commonly known as aspirin. This compound is commonly known as aspirin, and name of this reaction, like I said, this reaction is known as acetylation reaction. So this is example of acetylation reaction of salicylic acid. So this is the first part of the reaction that we have covered up, in which acidic strength and esterification we have done, where there was breaking of this OH bond. Now the second type of reaction, we are breaking of this carbon oxygen bond I am taking. So the next reaction here is reactions involving cleavage of CO bond in alcohols. First reaction here is reaction with hydrogen halides, which we have done in halalkanes chapter also. Hydrogen halide is HCl, HBr. Alcohols, they react with hydrogen halides, like in journal HX symbol I'm using. Water comes out and we get RX, haloalkane RX plus water. So now here question here is difference in the reactivity of primary, secondary and tertiary alcohol. Primary, secondary and tertiary alcohols. Distinction if we have to make. If three samples are given, one of primary, one of secondary and the third one is of tertiary alcohol, then how will distinguish between the three type of alcohols? For this we take the help of a test which is called Lucas test. For Lucas test, we use Lucas reagent. And what is this Lucas reagent? Equimolar mixture of HCl and zinc chloride. This mixture is known as Lucas reagent. So we will add this Lucas reagent into the three type of alcohols: primary, secondary and tertiary alcohol. This is tertiary alcohol I'm taking. Then this one is secondary alcohol. This is primary alcohol. To the all three alcohols we are adding Lucas reagent, that is HCl and anhydrous zinc chloride. Anhydrous zinc chloride. So I'm adding the Lucas reagent to these three type of alcohols. In this case, this water is coming out and in place of OH there is Cl. So reaction is taking place here. And this product that we are getting here, this is in the form of, you will say milkiness is there, that is turbidity. And immediately the turbidity comes in this case. The milkiness will come immediately on adding the Lucas reagent to tertiary alcohol. If we take secondary alcohol, in this also this water comes out. In place of OH there is Cl. In this case also turbidity will come, milkiness will come, but it will come approximately after 5 minutes, so you can write after some time. While in case of primary alcohol sample, when we add Lucas reagent, reaction will not take place here. So we can distinguish between the three type of alcohols. The sample in which turbidity will come immediately, we'll say that is tertiary alcohol. The one in which it will come after some time is secondary alcohol. The one in which we will not see any milkiness, that is a primary alcohol. From this test we can make out one thing more, that is reactivity order of the three type of alcohols. Tertiary alcohols are more reactive than secondary. Secondary alcohols are more reactive than those of the primary alcohols. So after reaction with hydrogen halides, next reaction now, dehydration reaction. Alcohols undergo dehydration. Like we take alcohol and for dehydration we use dehydrating agent, that is normally concentrated sulfuric acid, and we have to learn the temperature also of this reaction, that is 443 Kelvin. In place of this dehydrating agent we can also use phosphoric acid or anhydrous zinc chloride also. So this dehydrating agent will pull water from alcohol. So if from this carbon OH is coming, from the next carbon hydrogen will come, and between the two carbon atom there will be double bond. That means in dehydration reaction of alcohol, the product is an alkene. So there is alkene formation in the case of dehydration of alcohols. And alcohols, they undergo dehydration at a temperature of 443 Kelvin. Next is mechanism of this reaction. So reaction is in front of us. We can write the mechanism looking at the reaction. What will be the first step of mechanism? I told you before also, any reaction in which acid is used, normally H plus of acid that attacks the main compound and we will get the first step. So H plus attack on alcohol and it will form protonated alcohol, formation of protonated alcohol. So protonated alcohol will be by attack of H plus on this alcohol, CH3, CH2, and this is OH. O has electrons here, and H plus attack. So here in this case the attack is oxygen is more electronegative, so arrow will go from this side towards H plus. This H plus will add up with the oxygen. See, now lone pair is used by oxygen to combine with this H plus. O has used this lone pair, so positive charge will come here. This one is protonated alcohol. So first step is H plus will add up to alcohol and we will get protonated alcohol. Now come to step 2. Now in the reaction, see, there is removal of water. So from here we can remove water. Removal of water, and as a result of this, there is formation of carbocation. This water when comes out, this O is taking electrons from here, so this carbon will get a positive charge. That means we will get a carbocation in this step. Positive charge and plus removal of water. Now we have step 3, carbocation. In first step, there is a use of this catalyst. So in the last step, there should be removal of this H plus. So from this adjacent carbon, if H plus I take out without electrons, this bond will shift here. Double bond will come here and no positive charge now is left on this carbon. So it is HCH, double bond here, and there are 2 hydrogens with this carbon with removal of H plus. So we are getting ethene here in this reaction. This is a mechanism of dehydration of alcohols using an acid. So this is the second reaction. Now moving on to the third reaction, that is oxidation reaction of alcohols. If we take alcohols and do its oxidation, now depending on this oxidizing agent used here, it will oxidize to aldehydes, or if a strong oxidizing agent, then aldehydes further will get oxidized to the carboxylic acids. So reaction will stop at aldehyde or at carboxylic acid. That depends on the oxidizing agent. Example of strong oxidizing agents are KMnO4, and for mild oxidizing agent, CrO3 in acidic medium is used, or better one here is in place of this one is PCC, pyridinium chlorochromate. This can be used. It is also a complex of CrO3 with pyridine and HCl. So if we take, for example, this alcohol CH3, CH double bond, CH, CH2, OH, and add PCC here, that means it's a mild oxidizing agent. This will oxidize only to aldehyde with removal of this hydrogen. If we remove this hydrogen, this becomes CHO. So it will oxidize to aldehyde, CH3, CH double bond, CH, and then is CHO. So aldehydes will form here in this case. This is the primary alcohol. But if we take secondary alcohols like R, CH, R, and here we have OH, this is secondary alcohol. Secondary alcohols, they get oxidized, remember, to the ketones. R, C, R, double bond O. Again here removal of hydrogen, double bond will come here, and we are getting ketone with removal of hydrogen. And tertiary alcohols do not undergo oxidation. They do not undergo oxidation. So this is the oxidation. Now again, next reaction, that is also oxidation only, but it's a little different here. This is oxidation using the heated copper. Even silver metal can also be used here with heated copper. In this case, tertiary alcohols are also reacting. Primary alcohols oxidation with this will give aldehyde. Secondary alcohols oxidation gives ketone. But if we take tertiary alcohol, then there's formation of alkene. In this case, removal of hydrogen, but here we have a removal of water. Examples of these: primary alcohol reacting with copper, and temperature also we have to learn of this reaction, 573 Kelvin. There's formation of RCHO with removal of this hydrogen. So we are getting aldehyde here. Primary alcohols, they give aldehydes. Now secondary alcohol. This is example of secondary alcohol. Heating with copper, 573 Kelvin. They are forming ketone here. The product is ketone with the removal of this H2. Here we have a double bond. So we are getting ketone here from secondary alcohol by removal of hydrogen. But if we have tertiary alcohol, like suppose this alcohol we take and heat it with copper at 573 Kelvin. Now there's removal of water in this case from this carbon OH and from its adjacent carbon. All three are adjacent carbons. So from any one removal of hydrogen, and between the two carbons there will be a double bond now. So this becomes CH3. Next is CH3. And between the two these carbons there's double bond, and this is CH2 with removal of water. So here actually our product is an alkene. Alkenes they will form. So these are the chemical properties of alcohols that we have covered.